So as I mentioned before, first principles, the reason we call it first principles is it's the first thing we use so we can go and create formulas, which is going to save us some time. And that's what we're now going to do. Y equals a constant. Well, we already worked out that answer geometrically, but let's prove it using first principles. So function x is a constant. Function x plus h will also be a constant. So when we sub that into the formula, we get constant minus constant, which is of course 0. And the limit as h approaches 0 of 0 is 0. Okay. Y equals some constant times x. So a linear function. Again, we already know the answer to this one, but let's prove it. Function x is kx. X plus h becomes kx plus kh. Sub it into our formula. The kx's cancel. Kh on h. So we get the limit of k as h approaches 0. Well, that's just k. All right. Now let's prove one for any polynomial. X to the power of n. Now, in order to do this, I need to remind you of something. We know the difference of two squares. A squared minus b squared is a minus b, a plus b. We also saw difference of two cubes. A cubed minus b cubed. And then in the second one, the powers of a started going down by 1, powers of b going up by 1. So we got a squared plus ab plus b squared. And we said that that pattern continues. So if we wanted to, we could factorise a to the power of 4 minus b to the power of 4. It also would start with a minus b. But in the second one, it would now go a cubed, then a squared b, then ab squared, then b cubed. So a to the power of n minus b to the power of n will always start with a minus b, and then we'll go a to the n minus 1, powers are going down by 1, but meanwhile the powers of b are going up by 1 until we end up with b to the power of n minus 1. That's the one I'm going to need to use. Function x is x to the power of n. X plus h will be x plus h to the power of n. So when I sub that into the formula, there we have something to the power of n minus something else to the power of n. So I'm going to use that formula. So for A, I'm going to have x plus h. For B, I'm going to have x. So that will factorise to B. Well, it was A minus B. So that'll be x plus h minus x. Then the powers of x plus h will go down by 1. The powers of x will go up by 1. Now what's nice about that? X plus h minus h leaves us with just h, which will cancel with the bottom of the fraction. So now we're saying the limit as h approaches 0 of x plus h to the power of n minus 1 plus x plus h to the power of n minus 1, n minus 2 times x, and so on, sub in 0 for all of those h's, I get x to the power of n minus 1 plus x to the power of n minus 1 plus x to the power of n minus 1. Every one of those terms becomes x to the power of n minus 1. Question is, how many terms? Well, a squared minus b squared, we ended up with 2 terms. A cubed minus b cubed, we ended up with 3 terms. A to the power of 4 minus b to the power of 4, we ended up with 4 terms. So I think it's fair enough to conclude that we've got n of them. So anytime we want to differentiate x to the power of something, that power becomes the coefficient, and we take 1 off. We've now got a pattern that allows us to quickly differentiate any polynomial, and we don't have to use first principles. So let's have a look at a whole heap of examples, which hopefully will be very simple. We'll see. Y equals 7. 7 is a constant number. Differentiate 7, you get 0. Y equals 37x. Well, the derivative will be 37. Now, when you're writing down your answers, be very clear what is what. Just don't go 37x, which equals 37, because of course that is wrong. 37x does not equal 37. They are 2 different things. So label what they are. Y is 37x. The y dx is 37. X to the power of 10 now we can do. Bring down that power. We'll get 10 x to the power of 9. The nice thing about calculus is we can do each bit individually. So when we have several terms, we just differentiate each term. So 3x squared, but when I bring that 2 down, I can't get rid of the 3, it stays there as well. So 2 times 3 is 6, so we get 6x plus 6. Now, at this stage, we will see a rule later on, but at this stage, I can't do this. I'm going to have to expand it out first. So it's 4x squared plus 4x plus 1. So when I differentiate that, 8x plus 4. If function x is x cubed minus 3, find f dash 2. Now this is where you've got to make sure you're reading the question carefully. Very easy to misread that and just find function 2. That's not what the question's asking. So there's function x. We're going to have to differentiate it to get f dash x. That's 3x squared. Now I can find f dash 2. I substitute into that one and we get 12. So as I say, be very careful, read it closely, make sure you are answering the right question. Now a thing on notation as well, notice when I had y, I went to dy dx. When I had function x, I went to f dash x. So I tend to match the style of the question. Find the equation of the tangent to this curve at the point 1, 1. Y is 5x cubed minus 6x squared plus 2. Differentiate it. Remember, that is not the slope of the tangent. That's the formula that allows us to find. That's why sometimes we call it the gradient function. It's the function that finds the gradient. We want at the point x equals 1. Substitute in. We now know the slope of the tangent is 3. So the one we want is 3. Point slope formula. And eventually, I've got it in general form. 3x minus y minus 2 is 0. Let's find all the points on the curve. Well, so we've got a cubic, x cubed minus 12x, where the tangents are horizontal. So in other words, what we're trying to find is basically the turning points, because when it turns, you're going to have a horizontal tangent. Y is x cubed minus 12x. The derivative, therefore, is 3x squared minus 12. Again, explain what you're doing. Don't just go and solve this equals 0 and come up with numbers magically. Explain why you're doing it. So write down something like this. Well, I know the tangents are horizontal when the derivative is equal to 0. That is why I'm going to solve this equation. And we solve it, we get x is plus or minus 2. That's not the answer, of course, because they've asked for the points. So I need the y values as well. So when we set the x values in, I get 16 and negative 16. So there's my answer for that one. So that tells me, remember how we said cubics basically take on one of two shapes? Our traditional sort of shape there, or the one where it goes up and down? Well, this one must be one that goes up and down because we've ended up with two stationary points. Or is it down and up? Which one's this one going to do? Negative 2 16's up there, 2 negative 16 will be down there. No, it would be up and down, yeah. Bit of, definition here. A normal. So a normal is a line that is perpendicular to the tangent at the point of contact. There's the tangent, well, you'll know what that is. Well, the normal is the line perpendicular to it at the point of contact. So if they do ask us to find the equation of the normal, the first thing we've got to do is find the equation of the tangent. So y is 4x squared minus 3x plus 2. Dy dx, 8x minus 3. Again, that's not the slope of the tangent, that's the formula. We want x equals 3. So when x equals 3, the derivative is 21. So the slope I want, because we're not finding the tangent, we're finding the normal. So I want negative inverse. Minus 1 on 21. Point slope formula. 29 times 21. What on earth is that? Big number. There it is, 609. We'll put that into general form. But there's our equation of the normal that we're looking for. I did mention this earlier, but just to formally do it, a note on setting out. When you're differentiating, what you're actually doing is solving an equation. So we still obey the rule. What you do to one side of the equation, you do to the other. So technically this is what we're doing. When we see y equals x squared plus 2x, I'm saying I'm going to differentiate both of these sides with respect to x. Whatever I do to one side of the equation, I do to the other. So on the left-hand side, I'm saying I'm going to differentiate y with respect to x. Remember that other way I said we could write the derivative? D, whatever we're differentiating, with respect to, in this case, x. So on the left-hand side, I have d, well, it's y, I'm going to differentiate with respect to x. And on the other side, x squared plus 2x. So on the left-hand side, we just get dy dx. The right-hand side, differentiate x squared plus 2x, we get 2x plus 2. So you're actually solving an equation. You'll notice I've left a big gap there. What actually is happening is something called implicit differentiation, which we will look at later, don't panic. But what really happens is, when we say I'm going to differentiate y with respect to x, we actually go, well, whoa, hang on. I can't do that with respect to x. My pronumeral is y. So you go, all right then, I'll differentiate it with respect to y. But you can't change the question, just like any equation. So you've got to balance it out. And see, derivatives, remember, are rates, and rates are like fractions. So how do I balance it out so that it's still dy dx? Well, I'll multiply by dy dx. Because then theoretically the dy's cancel and you've still got the same thing. So now the question becomes, I'll differentiate y with respect to y. Well, differentiate y with respect to y, you get 1. See, if I had said differentiate x with respect to x, you would have gone, oh, 1. No different from another pronumeral. So now I'm saying 1 times dy dx, and that's why the dy dx is there. As I say, don't panic too much about that now. We'll look at that in a bit more detail later on. Of course, in reality, I just go y equals x squared plus 2x, and I write the answer down, 2x plus 2. What's important is you match the notation being used. That's what I was saying before. So if it says y equals, then I'm going to say dy dx equals. Or I might use the dash notation. So I might go y dash equals 2x plus 2. If it says function x, then I'm going to answer with f dash x. If it says d x squared plus 2x dx, then I'm just going to write the answer down, because I'm saying this is equal to 2x plus 2. Just like we see here. When we differentiated it, we just wrote 2x plus 2. So that's what we shall be working on.